This is Pre-Calculus, Chapter 1, Section 1.1, Day 1 Notes. We're going to start today by talking about sets of numbers. The first set of numbers that we're going to talk about is going to be the real numbers. And the real numbers are basically all the numbers on the number line. This set is represented by a symbol. We use a capital R with a double bar. Okay. A symbol. Because we can't list all of its members. So again, our notation for reals is going to be that symbol right there. So right now we're keeping it real. Okay, we're not going to be talking about imaginary numbers yet. We will get to that soon enough. So the next set of numbers within the set of real numbers is going to be the natural numbers. Another way that natural numbers are referred to is as counting numbers, because it's the numbers that we use when we count objects. So 1, 2, 3, so on and so forth. Please note that this set does not contain any fractions or decimals. And we are going to abbreviate natural numbers or notate it with a capital N. The next set of numbers that's a little bit bigger than natural is the set of whole numbers. We are going to denote that with a capital W. This set is represented by the numbers 0, 1, 2, 3, ... So notice the only difference between natural and whole is now we're adding in 0. So once again, this set still does not contain any fractions or any decimals. The next number set is the set of integers. We are going to denote integers with a capital I. So the integers are basically the whole numbers, but with positives and negatives. So we've got -3, -2, -1, 0, 1, 2, 3, and we've got that ... going in both directions, showing that it continues into the negatives and into the positives. But this set still does not contain any fractions or any decimals. Then the next set, getting bigger here, is the rational numbers. Rational numbers we are going to denote RAT. A rational number is a number that can be written in the form A over B, where A and B are integers. That's a fancy way of saying that a rational number can be written as a fraction. Okay? And what's important is that anything that can be written as a fraction, when you turn it into a decimal, the decimal form is either going to be terminating, meaning it ends, or repeating. So some examples of rational numbers that are either terminating or repeating decimals would be 4/5. 4/5 as a decimal is 0.8. It terminates. What about 1/3? Okay, so that is 0.3 repeating as a decimal. Or 1/4, that would be 0.25 as a decimal. So again, that one's a terminating one. So we have a terminating with 0.8, a repeating with 0.3, and then a terminating with 0.25. So then our last number set here is going to be the irrational numbers, which we are going to denote IRR for irrational. Okay, this is a number set. First of all, all numbers in the irrational numbers are numbers that are not rational numbers. Now, hopefully that makes sense. Irrational means not rational. The decimal form of an irrational number is going to be a non-terminating or a non-repeating decimal. Okay? Decimals that never end and never repeat are irrational decimals. So some examples of some famous ones: pi, that's one of our very favorite irrational numbers. Also, e is another one. And we haven't talked about it yet, but any square roots, cube roots, fourth roots, any radical numbers, so like square root of 7, that's going to be an irrational number. Now keep in mind, if there's a perfect square under a square root, that's not irrational because it simplifies to a whole number. But square root of 7, square root of 8, square root of 10, square root of 11, so on and so forth, those are all going to be irrational numbers. So now that we know our number sets here, keeping in mind that natural, whole, integer, rational, and irrational all fall under the real numbers. So perhaps I should have put real at the bottom instead of at the top. When we talk about numbers, they can belong to multiple number sets. So next we have some examples where I've given you some numbers and I want you to tell me how many sets do these numbers belong to. Well, 14.2 is a real number. Okay? Everything right now is real. Not real is imaginary. We have not started talking about that yet. So 14.2 is real. Now keep in mind, the natural, the whole, and the integer, all three of those do not contain any fractions or decimals. So we know 14.2 can't belong to any of those three. But it has to be either rational or irrational. And here's another important thing to note. A number can't be both rational and irrational. It's one or the other. So the question is, it's in decimal form, 14.2. Does that decimal end or repeat? Why, yes, it does. So that makes it a rational number. Number 2, the cube root of 5. First of all, it is real. We could plot it on the number line. Is it rational or is it irrational? Well, I just got done saying a few minutes ago that radicals are irrational. Then finally, we've got natural, whole, and integer. It can't belong to any of those number sets because the cube root of 5 is a decimal when we transform it, and those don't have any fractions or any decimals in them. Last one, 127, definitely real. It can be written as a fraction, so it is a rational number. It is not currently a fraction or a decimal, so it belongs to the natural because it's a counting number. It belongs to the whole, and it belongs to the integer number set. So the only one that 127 doesn't belong to is irrational numbers. Okay, finally we have our properties of numbers here. And again, these are things that you should be familiar with. You've seen them in Algebra 1 and Algebra 2. We've got the commutative property of addition. That says A plus B equals B plus A. Of multiplication, that's going to look like A times B equals B times A. So either way, this property allows you to change the order. The associative property looks like parentheses A plus B plus C, and that's equal to A plus parentheses B plus C. We can do the same thing with multiplication. We can say A times B times C is equivalent to A times B times C. Now notice here we are moving the parentheses. So that's what the associative property allows you to do. It allows you to move the parentheses in your expression and still have an equivalent expression. The identity property of addition says you can take a number, you can add 0 to it, and you still get that same number. The multiplication property, or the identity property of multiplication, says you can take a number, you can multiply it by 1, and you still get that number. Our inverse property says if you take a number and you add to it its additive inverse or its opposite, you will get a sum of 0. The inverse property of multiplication says if you take a number and you multiply it by its reciprocal, you will always get 1. And then finally, our distributive property, that one we all know and love. If we have A times parentheses B plus C, we can distribute that A, and we end up with A times B plus A times C. So now let's look at a few examples and try to identify what property we see. In example 1, we have 7 times 8 is equal to 8 times 7. Notice that we're changing the order here. So this is going to be, I'm just going to abbreviate, the commutative property of multiplication. In number 2, we're taking 15, we're adding 0 to it, and we still get 15. That is going to be the identity property of addition. In number 3, looks like we have parentheses on the left, and we don't have parentheses on the right. We have distributed that 5 to the 7 and the x. So this one is going to be the distributive property. Number 4, we have multiplication on both sides, and it looks to me like we're changing our grouping. We're moving our parentheses. When we move our parentheses, that is the associative property, and in this case, it's of multiplication. Number 5 is a little bit of a trick. We have parentheses on both sides of the equal sign. Notice we're not moving the parentheses. We're not changing the grouping here. So it's a little misleading. You want to say associative property, but it is not associative property because the 7 is outside the parentheses on both sides. But notice that inside the parentheses on the left and the right, we're changing the order of the terms. On the left side, we have 4 plus x. On the right side, we have x plus 4. The property that allows us to change the order is the commutative property, and this is addition. And then number 6, we're adding w to negative w. We're adding a number, and it's additive inverse. So this is the inverse property of addition. Finally, we finish this out here with a little bit of a fraction review. Remember, when we add and subtract fractions, we need to find a common denominator, CD. So if we're going to add 2/3 plus 4/5, we need a number that 3 and 5 both go into. The smallest or least common denominator for those two numbers is going to be 15. So the first thing I'm going to do is I'm going to make 2 new fractions that has 15 in my denominator. Now whatever I did to my old denominator to make the new denominator, that's what I have to do to my numerator. Looks like I multiplied 3 by 5 to make 15, so I'm going to multiply 2 by 5, and that's going to give me 10/15. Then the second fraction, I multiplied 5 by 3 to make it into 15, so I'm going to multiply 4 by 3, and that's going to give me 12. So now I have 10/15 plus 12/15. That's going to give me an answer then of 22/15. As long as your answer is in lowest terms, improper fractions are just fine with me. All right, number 2, it looks like we're adding 2 mixed numbers. Now remember, when you're adding mixed numbers, you have the whole part and you have the fraction part. So I think the easiest way to do this is let's just pull out those whole parts and say, well, first we've got 4 and we've got 5. Let's add those together. So that gives us 9. Then we still need to add the 3/4 plus the 1/6. Okay, well now I just need a common denominator for 4 and 6. You could say 24, but that's actually a little bit too big. That's kind of overkill. You'd have reducing to do because 4 and 6 actually both go into 12. So I am going to use 12 as my common denominator. 4 goes into 12 3 times, so I'm going to multiply 3 times 3. That gives me 9. 6 goes into 12 twice, so I'm going to multiply 1 times 2. That gives me 2. And then when I add 9/12 plus 2/12, I get 11/12. So my final answer is going to be 9 and 11/12. Finally, we've got multiplication and division, which are actually easier than addition and subtraction. Now remember, when you multiply, you are just going straight across the top and you're going straight across the bottom. A lot of people get confused about cross multiplying versus straight across multiplying. So you're going to multiply numerator by numerator and denominator by denominator. But we do have to change something here first. Notice we've got a mixed number, so we need to change that to an improper fraction. Remember, you do the denominator times the whole number and add the numerator. So this is going to be 3 times 5, which is 15, plus 1, which is 16. So this is going to be 16/3, and then here I've got 7/40. Okay, now I'm going to do a little bit of reducing up front. I like to reduce before I multiply versus after. So I look at 16 and 40 and I say, well, those can both for sure be reduced, and they have a common factor of 8. So if I divide 16 by 8, this becomes a 2, and if I divide 40 by 8, this becomes a 5. Now I'm going to multiply straight across. 7 times 2 is 14, and 5 times 3 is 15. That can't be reduced because I already reduced up front. Final answer is 14/15. My last example here, I've got I've got division, and then I've got subtraction. So I'm going to start by doing the division first. This is 4/1, but I'm going to, for divide, remember I am going to keep, switch, flip. So this is really 4/1 times 3/5 which gives me 12 fifths. And then I'm going to bring down